All right, today we're jumping into a classic autumn mystery. We've got a suspect, the humble pumpkin, and we've got a crime, its wild, fluctuating price. Our weapon of choice, machine learning. But the real question is, do we even have enough clues to crack the case? So, here's the big question that's going to drive our whole investigation. It seems way too simple, right? Can just one piece of information, the day of the year, actually be enough to predict the price of a pumpkin? Let's find out if this one clue is the smoking gun we need. You know how every good mystery starts? With the evidence. For us, our evidence locker is a data set just packed with pumpkin prices. So, let's put on our data detective hats, dive into these numbers, and see if we can uncover the pattern hidden inside. Okay, let's open up the evidence file. The case is pumpkin price prediction. Our main piece of evidence, our key clue, is just the day of the year. Now, our first look at the data gives us a weak negative correlation, a minus 0.27. So what does that mean in detective speak? It's a hint. It suggests that as the year goes on, prices tend to dip a little. It's not a confession, but it's our first real lead. And any good detective knows you follow every lead.
So, we've got a lead. What now? Well, every detective needs a theory. Let's start with theory number 1, the straight line. What if this relationship is super simple, a straight line? As the days tick by, the price just changes at a steady, predictable pace. In the data science world, we call this simple theory linear regression.
So what exactly is linear regression? Honestly, just think of it as a tool that tries to draw the straightest possible line through a messy collection of data points. It's on the hunt for a simple, constant pattern. As one thing changes, the other thing changes by a consistent amount. That's it.
And how do we actually test this theory? Well, we follow a pretty standard process. First, we get our clues ready, just the day and the price. Then, and this is super important, we split the evidence. We use most of it to train our model, kind of like teaching it what to look for, but we keep a little bit separate for testing it later. Why? Because we need to see if our theory holds up against evidence it's never seen before. No cheating allowed.
All right, the model has done its homework and the predictions are in. This is the moment of truth. Let's dig into the evidence and see if our straight line theory actually solves the mystery, or if we're headed right back to the drawing board. And oof, right out of the gate, the evidence is not looking good. We've got a mean squared error of 17.2%. Now this number is basically a score of how wrong our predictions are on average. So being off by 17.2%, that's like having a witness whose story is full of holes. Not exactly reliable.
But this next number, this is even more damning. It's the R-squared value, and it tells us how well our theory explains what's actually happening. A perfect score is 1. We got 0.04. Yikes. That is incredibly low. It basically means our straight line theory explains almost none of the price swings we see in the real world.
If you were to plot this out, you'd see it immediately. You'd have this big, scattered cloud of dots showing the actual prices. And then you'd see our prediction, just a single straight line cutting right through the middle, missing almost all of them. The visual evidence totally confirms what the numbers told us. Our theory just doesn't fit the facts.
And the source material really hits the nail on the head here. It says the vertical distance between the points and the prediction line does look pretty significant. That vertical distance is our error. It's the gap between our theory and reality. And right now, that gap is a chasm. So case closed on this theory. It's officially busted.
But hey, a good detective doesn't just pack up and go home after one failed theory, right? If a straight line doesn't work, maybe the real pattern is more curvy. What if the relationship isn't a simple line, but a more complex curve? This leads us to theory number 2, polynomial regression. So what's the big difference here? It's actually pretty simple. Linear regression is like a ruler. It can only draw straight lines. It's rigid. But polynomial regression? That's more like one of those flexible rulers you had in school. It can bend and curve, which means it might just be able to capture a more complex, realistic pattern in the data. So it's round 2. We're running the investigation again. We've got the same evidence, same process, but this time we're giving our model a new tool. We're letting it look for a curve in the data instead of forcing it to find a straight line. We check the new results and, okay, the mean squared error dropped to 17.0%. I mean, yes, that is an improvement, but it's a tiny one. We're still pretty far off the mark. Our new, more flexible theory is only a little bit better than our first one. And what about the R-squared value? It's up to 0.08. Now, yeah, that's double what we had before, which sounds good. But let's be honest, doubling a really, really bad score still gives you a bad score. Our curved line is a better fit, sure, but it's still an awful fit overall. This case is far from solved. So, we've pursued two theories, we've analyzed all the evidence we have, and now it is time for the final verdict. After all this, what did our pumpkin price investigation actually teach us?
This summary table lays it all out, crystal clear. Theory 2, the curve, was a little bit better than Theory 1. The error went down a tiny bit, the model fit doubled, but look at the final verdicts. Poor fit versus slight improvement. Neither one of those sounds like we cracked the case, does it?
And that's the final verdict. Neither a straight line nor a simple curve can reliably predict the price of a pumpkin, not when we're only using the day of the year. The real relationship is just way more complex than our one little clue can handle. And this is the real plot twist, straight from the source material. The problem might not have been our theories at all. The real problem was our lack of evidence. We've been trying to solve this entire mystery with just one single clue. And that brings us to the most important question of all. What other clues are we missing? What about the city or state where the pumpkin was sold? The size of the pumpkin, the specific variety? How about the weather that year? This whole investigation teaches us a really important lesson. In data science, just like in detective work, sometimes the key to cracking the case isn't finding a more clever theory, it's just going out and finding more clues.